Our bell ringer today is, what is the reaction quotient for the reverse reaction of 2KOH plus H2SO4 yields K2SO4 plus H2O? So the reverse reaction quotient. Pause the video, write it down, double check. Hopefully you are able to say, well, when we're dealing with a reverse reaction, that simply means our products become reactants and our reactants become products. So the reverse reaction quotient will look like KOH squared times the concentration of H2SO4 divided by the concentration of K2SO4 times the concentration of H2O squared. Today we're going to be talking about how we can express equilibria in terms of pressure. And so our learning objective is I can calculate the equilibrium constant with respect to concentration and the equilibrium constant with respect to pressure using their relationship through the ideal gas law. So up to this point, we've talked about everything in terms of concentration. However, it is much easier to measure the pressure of gases than it is to measure the concentration of gases. So it can be very useful to relate pressure to concentration through the ideal gas law. If you need a refresher, it's right up there. PV is equal to nRT, where P is pressure, V is volume, N is the moles, R is the universal gas constant, which is 0.0821 atmospheres times liters per moles times Kelvin, if you're working in atmospheres, times temperature. If we rearrange that, so we've got P divided by RT is equal to N divided by V, we can see that the pressure P is directly proportional to our molar concentration N. This gives us some pretty good flexibility to relate pressure and concentration, especially when we're dealing with things like equilibrium. So we can express our equilibrium constant, Kp, based on pressures. It is a different numerical value than our equilibrium constant with respect to concentrations. But if you know one, you can calculate the other. And we're going to derive on the next slide how exactly we do that based on our ideal gas law. But we're going to need one more piece of information, and it's the easiest calculation you've ever seen in chemistry. It is the change in the amount of gases. So that simply means delta N gas means you're going to take the sum of the moles of the products of gases. So that just means adding up all of those coefficients. Subtract from it the sum of the moles of gases in the reactants. We're going to work with the equation 2NO gas plus O2 gas yields 2NO2 gas. And the first thing we're going to do is we're going to, hopefully this is somewhat for a memory refresher, but if not, that's just fine. We're going to talk about how we can express our reaction quotient in terms of pressure. We've discussed up until this point things only in terms of concentration, but here we're going to be able to see how we can write our reaction quotient, so our ratio of products to reactants, but with respect to pressure. It's not too complicated. It's going to look very, very similar to what we're used to. We're going to take the partial pressure of all of our gases. And so when we're starting off, we're writing our products in our numerator. So the partial pressure of NO2, but this is going to be squared because there's a coefficient of 2. And then in our denominator, we've got the partial pressure of NO gas, also squared because of that coefficient, times the partial pressure of O2 gas. Not too complex. but a good thing to know, and it will be important in our next step when we actually work through the whole derivation. So, as I've said for several slides now, let's get into the actual derivation. Our first step is going to be to identify our delta N, or our change in the amount of gases. So, we're going to look over here. We see that we've got 2 moles of gases in our products. Subtract from that the sum of the moles of gases in our reactants. We've got 2 here. Remember, when we don't see a coefficient, that doesn't mean a coefficient of 0, that means a coefficient of 1. So 2 minus 2 plus 1 is 3. It's going to be negative 1. Then what we're going to do is we are going to express our concentration as partial pressures in the reaction quotient. So here is our reaction quotient expressed in terms of concentration. However, we are going to use the relationship between molar concentration and partial pressures to rearrange this. So remember, that relationship is the moles divided by volume is equal to pressure divided by R times T. So that is going to look like this. We have our moles squared of NO2 per volume squared over our moles squared of NO per volume squared times our moles of O2 per volume squared. And that, because we're relating our molar concentrations to partial pressure, is going to be equal to pressure squared of NO2 per RT squared over partial pressure of NO squared per RT squared times the partial pressure of O2 divided by RT. So if we then simplify this a bit and we convert, so now we've done the first step essentially of initially we expressed our concentration as molar concentrations. We have now converted it into our partial pressures. Once we have this, the partial pressure form, what we can do is pull out all of those RT forms, or all of those RT expressions, so that we can simplify this and make it look a little nicer. So when you separate the partial pressures from the RT terms, this is what you should get. We will have the partial pressure of NO2 over the partial pressure squared of NO times the partial pressure of O2 is equal to 1 over RT squared over 1 over RT squared times 1 over RT. So what we can do now is we can simplify this a little bit further yet. We have our partial pressures are equal to, our partial pressures are not, and that will look like this. We have the partial pressure squared of NO2 divided by the partial pressure squared of NO times the partial pressure of O2 times 1 over RT squared divided by 1 over RT squared times 1 over RT. And we can actually simplify this a bit further. We can cross out these RT terms because 1 over RT divided by 1 over RT, those are going to cancel out. And because this is in the denominator, we can actually flip it around and figure out how it is going to look. And when we simplify further, we will see that our partial pressure NO2 squared over the partial pressure squared of NO times the partial pressure of O2 times RT to the negative first. So that would be 1 over RT, or RT to the negative first. So when we look at all of that simplified, we can see that our reaction quotient with respect to concentration is equal to our reaction quotient with respect to pressure times RT. And when we're looking at equilibrium, so that would be our reaction quotient at equilibrium, we know that that is equal to our rate constant at equilibrium with respect to concentration. So our rate constant at equilibrium with respect to concentration is equal to our rate constant with respect to pressure times RT. If we rearrange that just a little bit more, we can see that our rate constant with respect to pressure is equal to our rate constant with respect to concentration divided by RT, or Kp is equal to Kc times RT to the negative first. So this particular derivation has shown us that our rate constant with respect to pressure is equal to our rate constant with respect to concentration times RT to the negative first. However, we are going to take this a step further because we're not only going to be working with 2NO gas and O2 gas. So what this actually shows us is that our rate constant with respect to pressure is equal to our rate constant with respect to concentration times RT to the power of our change of gases, change in the amount of gases. So Kp, our rate constant with respect to pressure, is equal to our rate constant with respect to concentration times RT to the delta N power. Let's take a look at a quick practice problem. This is 17.27 from the textbook. Determine the change in the amount of gases for each of the following reactions. All right, let's take a look at A. We have 2KClO3 solid plus H2 gas yields 2KCl solid plus 3O2 gas. So the first thing to remember here is that we're only looking for the concentration, or we're only looking for the change in the amount of gases, not in the amount of our solids. So our delta N gas is going to be equal to, let's look at moles of gases in our products. 3, and we're going to subtract from that moles of gases in our reactants. So we only have one gas, coefficient of 1. 3 minus 1 is equal to 2. So that would be the power to which we raise R times T if we were going to use this to calculate our reaction, or our equilibrium constant, with respect to pressure. When we look at example B, we've got 2 PbO solid plus O2 gas yields 2 PbO2 solid. So our change in amounts of gas is equal to 0. We have 0 gases in our products, minus 1 for our O2 in our reactants. Our exponent would be negative 1. And finally, C. We've got I2 solid plus 3XeF2 solid yields 2IF3 solid plus 3Xe gas. So here we have 3 moles of Xe gas minus 0 moles of gases in our reactants. Our exponent would be 3.